Hi everyone. So we're actually going to go over the Algebra 2 Semester A first tutorial, which is in Unit 1, Expressions. This is a little bit of a review from Algebra 1, where we're going to go ahead and look over expressions. Remember, the key difference between an expression, it looks exactly like an equation, but it does not have an equal sign. So we're going to go ahead and take a look at that, starting with the warm-up on slide 5. So keep in mind, while you're watching this video, you can go ahead and pause and work on it on your own or follow along and take notes. I will definitely point out where you should write down formulas or rules to keep in mind to help you to move on to the next sections, like the practice and mastery tests. So let's go ahead and take a look at the warm-up here, slide 5 again. So here we have some vocabulary words so we can go over. Keep in mind, a term is pretty much the broken pieces, or for example, let's use the actual problem right there, w squared plus 5w. This expression right here has two terms. This is considered one term. This is another term. So that's 1, 2. Another example for a term would be like 3x minus 1. This is considered a term. This is another term. What is considered an exponent? So an exponent is normally found with a variable, sometimes with a just a regular number as well. We can have x squared, and this 2 right here is an exponent. You can have 3 to the 4th power. That is the 4 right here is an exponent as well. You can have a to the 5th power. And again, that 5 is your exponent. What is considered a constant? A constant is just a regular number. So here it doesn't look like we have one, but if I say x squared plus 3, my 3 is my constant. So it's just a number, no variables. An expression, it looks very similar to an equation. An expression will not have an equal sign. An equation will have an equal sign. So if I bring back my x squared plus 3 here, I can say this is before, that's considered an expression, x squared plus 3. But if I want to make it into an equation, I can say x squared plus 3 equals 10. That's an equation. What are my variables? Pretty much our variables are any letters that we find in an expression or in a equation. And coefficients is, let's bring up another example. Let's say 2x squared. This 2 is the coefficient for x squared. If I have 3x, and again, remember, these variables can be represented in different letters. So this 3 would be our coefficient for x. So now that we kind of got a little refresher, right, from Algebra 1, we can kind of go back into here. So what is w squared plus 5w? Well, also, if you take a look at it, I'm horrible, but sometimes I tend to skip the directions here, but it's like, don't do that. Match the math vocabulary words to parts of the expression w squared plus 5w. So they kind of already gave you away one answer. Your w squared plus 5w is considered an expression. The w in w squared plus 5w. So what is considered the w? Remember, it's a letter, or in other words, we can call it our variable. It says the next one is the 2 in w squared plus 5w. Well, the 2 is only found in w squared, and that is raised to in a power. So power, or our exponent here. The 5 in w squared plus 5w. So this 5 in front of 5w, remember, when you have a number in front of a variable, that is the coefficient. There is one more hint that I want to make sure we all remember, is that w squared does have a coefficient as well. The only thing is we don't acknowledge it, or it's there, but it's invisible. So w squared plus 5w can be rewritten as 1w squared plus 5w. So all the variables have some type of coefficient in front of it. But if there's not an actual number listed, it is most likely going to be our invisible 1. So don't forget about that. The w squared, or the 5w. So here they're kind of breaking it up into little parts. And if we look, we either have term, a constant, or equation. We know it's not a constant because there's no regular numbers there. It's definitely not an equation because there's no unequal sign. So our only thing left there is term. So remember, this expression has two terms, which is w squared plus 5w. Let's go ahead and move on to the next slide. So Bella's family is building a patio in the backyard. The width of the patio is W. The length of the patio is 5 feet longer than the width. So we're going to be given some type of word problems here. And here they already gave it to us, but keep that in mind when the way they word it, because that's going to be super important. So they did tell us that they're pretty much basing everything off of the width, right? We don't know this length of the patio because it depends on our width, but we do know that the length is 5 feet longer. So 5 feet longer, that's why we have that plus 5 to that W there. So pretty much this is the example that we're going to kind of be seeing throughout the tutorial. And keep in mind, so one way to show the area of the patio is W squared plus 5W. How did they come up with that? And that's pretty much the same expression that we had in our warm-up. How did we get this as our area? So remember, the area of a rectangular prism this is our length, and we'll just have width again as a W. So we have A equals the length times the width. Keep in mind the length here is, I'm going to put this in parentheses because it's just a whole chunk right here, W plus 5 times W itself because that represents width. Now here, we can still simplify this. I don't like to see those parentheses there, so let's remove the parentheses by distributing that W inside the parentheses. So W times W, that is our W squared. Let's keep that same plus sign there. W times 5 is 5W. Matches exactly to what they gave us here. So pretty much they already distributed it for us to give us the area. Moving on to slide 7. So we're going to be interpreting those expressions. So what do we mean by interpreting? We're going to be given a verbal description. And with that verbal description, we have to come up with an expression for it. So here they give us an example, 2n minus 7. 2n minus 7 can be rewritten in 3 different ways verbally, right? So the first one is the difference of twice a number and 7. So with these, I like to break them up, especially this one is a simplified one. There could be more to it. So you got to learn how to break it down as much as possible in order to help you out with that. So let's take a look at the first one. So when they say the difference of, the key word right there I'm going to look at is of. Anything after of is what's going to happen in between. So right here, when I hear the difference, okay, think of my minus sign. And then it says of, so this is going to be part of the difference. Twice a number. So twice a number is, in our heads, we can think of 2 times a number. A number is going to be our variable x. Or in this case here, we'll go with what they have here as n. Twice a number n. So twice or 2 times a number n, right? And, so that's the keyword where your minus sign should go because that's the difference, 7. So it's exactly how it matches up to this. Again, you can rewrite these in couple different ways. Second one is 2 times a number decreased by 7. So again, 2 times a number, we kind of already saw that a little bit over here, right? Twice a number, 2 times a number. So 2 times a number decreased. So when we think of decreasing, we're subtracting, right, by 7. Third one, 7 subtracted from. So these a little bit, it's kind of like you're going to swap it because a common mistake here that happens is that the 7 gets written down first. But remember, you're subtracting 7 from the product. So the product is, again, multiplication, right, of 2 and, so that's your keyword for where your multiplication symbol should be, right? 2 times a number. So we have 2n. But remember, we 7 subtracted from 2n. So 7 is subtracted from this product of 2 times a number. So we'll be interpreting them. Again, I like to use their examples here and go along with you. And then make those notes. Again, I will point out where you want to make those notes. But let's go ahead and take a look at this one. So it says translating description into an algebraic expression, understanding the meaning of the mathematical words and phrases. So if we click on this link, we're going to be given, here we go. So this one is a kind of like a little chart. You can have it up for yourself, but we should, the sum, when you hear the sum of, that represents our addition, right? The difference of, less than, that's your minus. Product, you'll most likely hear product, that's your multiplication symbol. And then the quotient, it is your division symbol. So you can refer back to that link to go ahead and make notes of it or take a screenshot. But let's go ahead and take a look at this one right here. Give me a second. Oops. Okay. So it says 6 multiplied by the absolute value of 7 less than the cube of a number. So let's go ahead and work on that together. So we know 6 multiplied. So we're going to have 6 times something. Now the next thing it's telling me is the absolute value of. So when we have we're going to go ahead and put our absolute values symbols there. The thing is, we don't know exactly what goes inside. But remember, after it says the absolute value of, that after whatever happens after of is going to be inside my absolute value symbol. So the absolute value of 7 less than the cube of a number. So 7 less than a cube of a number. This is, remember how it's going to go a little bit reverse. So I know it's going to be 7 less. So I'm going to put my minus 7 back here. Cube. So that represents our exponents to the third power. And here we can put a number. It looks like we might be, we can put x. If we click along, it'll probably give us a different variable. Maybe, maybe not. Okay, so we came up with the same symbol or the same expression, but we used x instead of n. But again, you want to make sure you're able to take that verbal description and break it down into pieces. Sometimes when we speed read, right, or when we just read, we're like, what in the world happened right there, right? So here we just want to make sure we break it up into parts. So let's go ahead and take a look at the next slide on slide 10. So here we're going to be given some examples, right, of verbal descriptions, and we're going to go ahead and match them up. So it says the absolute value. So absolute value, again, we know we have these two absolute value signs right here. And it says absolute value of. So after the word of, right, that's going to go inside my absolute value. Twice a number. So we have 2 times, well, our number looks like it's going to be representative of x. So twice a number, increase. So if I want to increase something, what we need to think about the symbol here. It's going to be plus, right? Increase is plus by 11. So that matches this one right here. Also, if you do kind of like a process of elimination, that is your only expression that has a absolute value symbols. Let's take a look at the next one. The square root of. So again, here's my of. Everything after of is gonna, so this piece right here, right, is gonna pretty much go inside my square root. So let's go ahead and draw a square root button. The difference of the square, so the difference, so we have a minus in there, of the square of a number. So square of a number, the square root of the difference. Oh, let me take that back for a quick second here because I am messing up on my own ofs. So the square root of the difference of a square of a number and 11. So I actually was on the right track. I just second guessed myself here. So the square root of the difference of, so there's always of, the square of, the difference of, there's multiple steps in here, of the square of a number. So again, when they say number, we're just going to represent that as x, the square of a number, and 11. So that is this expression right here. Oops. Okay, let's take a look at the next one. So it says the quotient. So you can always go back to that one chart where it gave you a list of expressions and keywords. But normally when we hear the word quotient, we are dividing something. The quotient of 2 times a number. So 2 times a number. Oops, that's supposed to be my x. 2 times a number and negative 11. So even though that negative belongs to that 11, because it kind of stated there, your negative can actually move to the front of it. Plus, again, that's your only expression that has a quotient. The next one is the sum of a square root. So just to kind of go with continuing on, when you hear the keyword the sum, what symbol do you think of? And if you take me look at your two expressions, there's only one that represents a sum. So go ahead and drag that along and go ahead and submit. Again, let's go ahead and move on to slide 11. Evaluating expressions. So when we are evaluating expressions, we're going to have an expression and and remember, an expression can have our variables in there. We don't know what the variable it represents. We don't know what number, but here they are going to tell us a number. So right here, if we take a look at this one, it says, for example, the area of Bella's patio depends on the value of W. The width. Let's find the area of the patio if the width is 12. So right here, the width is 12. That's telling me W is equal to 12. So what we can go ahead and do is that we're going to take our area here, right? Because we know area is equal to W squared plus 5W. We're going to go ahead and wherever I see a W, I'm going to replace that with 12. So you can write it out like parentheses like this if you're not too comfortable and you want to make sure. So do you see every single time I saw a W, I put a separate parentheses. And that's where we're going to, inside those parentheses is going to be our 12. So right here we have 12 and we have 12 here. So now keep in mind, here we just go ahead and simplify, right? 12 squared is 144 plus 5 times 12 is 60. And once we add these together, we get 204. 410, yes. So we get 204 as the area, well, 204 feet squared, because again, that represents the area of the patio. So again, as we follow along, they did the same thing. They're substituting that W, or substitute, pretty much replace a W, right, with 12. And you're going to go ahead and continue simplifying, and you get the same answer. Again, if I go too fast, you can always go ahead and pause it. I highly suggest trying to do it on your own before you're watching like the next part of it, to go ahead and practice it. So let's go ahead and move on to the next one. So slide 13. Bella has two expressions for the area of her patio. They have the same value. Let's test that. Substitute the width of 12 into each expression. So remember, if you think about it here, we should still get the same results because this was our setup. W parentheses W plus 5. Here we can agree that it's similar to this one. The difference is that the one on the right-hand side, W plus 5, we distributed that W outside of the parentheses inside to get the one on the left, which is W squared plus 5W. Are we going to get different values when we replace W again with that 12, which we did on side 12? Technically, there's no difference. It is the same expression. It looks a little bit different, but it's the same thing. Kind of like when I say tomato, you say tomato, same idea, right? We're talking about the same fruit, but it is represents it's the same expression, just it looks a little bit different, kind of like that expression, right? You say it differently compared to me, but we're still referencing to the same problem thing. So let's talk about this one on slide 14. So now we have an expression 3 times the absolute value of x cubed minus y squared. So here they do tell us, again, this is a whole part of the evaluating part. They're letting us know that x is -3 to the third, or x equals -3. I'm already jumping ahead, and y equals -5. So again, we're going to replace it. So I'm not going to do parentheses because I feel like it might just add more clutter to it. Uh, I actually will add parentheses when we need it, especially here. So let's rewrite this expression, but let's go ahead and add the information we already know. So this is 3. We have the absolute value of x to the third power. Because I have these negatives, I'm going to put those parentheses. I take that back where I said I will not put them. I will put them there. Minus, and then this is y squared. So again, all I did was just substitute those variables that we have with the values that they told us. Now we just simplify this. Now I want to concentrate where I have those parentheses because I want to remove them by actually applying that power. So we take a look here. This is 3, that 3 on the outside. I'm going to still keep my absolute values on the inside here. But what is -3 to the third power? So we're a little rusty on exponents. Keep in mind, -3 to the third power is equivalent to -3 times -3 times -3. So I write it out 3 times because of that exponent there. So 2 -3's is a +9 times one more -3. That is -27. Minus is still there. -5 squared. Again, if that's just telling us that it's -5 times -5, which is +25. So please be very, very careful with those negatives because if we left the negative on the outside, we would end up having a double negative, making it +25. So it's like, I know I want to try to step away a little bit from the parentheses by substituting. It's sometimes best to place it there just to be careful with those signs. So back over here. So we're going to go ahead and take another look at it again. And 3 times the absolute value -27. Well, keep in mind, we have 3, the absolute value of -27. Remember, absolute value is how much are you away from 0? Or you can think of it another way, as in when you have absolute value, it's always going to be that number, but positive, always positive. So here we do have a -27. Keep in mind that is going to be a +27. So after you take the absolute value, the negative gets removed. Then we still have this -25. And it's like, and we're following pretty much PAMDAS. Please, if you haven't heard of it, right, please excuse, this is probably the only way I remember it. Please excuse my dear Aunt Sally, right? We took care of the parentheses first, which was right here with the exponents, which covers our E. We are multiplying right now. There is no division. We would add next, but I don't see there's no addition there. And then that final step would be subtracting. So right here, so the next part is multiplying 3 times 27. So 3 times 27, it is 81. Then I bring the rest down. So 81 minus 25. So when we subtract that, we get 56. So you're going to be given some expression. We're going to tell you what those variables, what numbers those variables represent. You'll substitute or plug in and then simplify. So let's go ahead. So this whole little description that I gave you right here, that is what they did if you follow along with these next couple of slides. So they substitute They were simplifying and continue to simplify, and they got the same value, 56, just like we did as well. So again, you want to make sure you follow that order of operations, which I like to say is just PEMDAS. So if while you're like following along with this video and also working on your tutorial, make sure again you take those keynotes. Like I said, I'll point about. You definitely want to point out PEMDAS and make sure you have it there and kind of follow through when you're solving these expressions. Let's take a look at slide 15. We have that same example here, right? It is 4 times the square root of a squared minus b squared. So they do tell us again our value. So what we're going to go ahead and do is let's go ahead and do our setup. 4 times square root. I have my first variable there, which is a. I'm going to put parentheses for my a, and don't forget the 2, the squared. A is -5, so we're going to go ahead and put -5 right here. There's our minus. Now, again, we have our second variable here, which is b. I'm going to put parentheses squared, like b squared, but our b is going to be replaced with 3. And again, we simplify. I would simplify those parentheses first. So when we go ahead and continue, we have 4 parentheses, right? The -5 squared. Remember, it's -5 times -5, which is positive 25. Let's keep our minus there. 3 squared is the same thing as 3 times 3, which is 9. And then here we have 4, the square root of, let's go ahead and subtract that inside. So I know when we're trying to follow PEMDAS, right? Subtraction is kind of like towards the ending, and there's nothing about mentioning of a square root, but you want to try to condense everything as much as possible, especially in here with the square root. So 25 minus 9, it is 16. Let's take the square root of 16. So we'll have 4 times 4, which is 16. So you'll go ahead and enter that down below. Again, make sure you pause the video if I went a little too fast. You can always pause or go back if there was something that didn't make sense. So let's take a look at properties of exponents. So again, it's a little bit of review from the Algebra 1 class. And we so far looked at those expressions. Now we're going to look at the properties of exponents. So again, the things that I want you to make sure you keep in mind, this rule is super important. B to the 0 power is equal to 1. Anything raised to the 0 power will automatically be 1. So I can have 205 raised to the 0 power. You're going to go ahead and say that's going to be 1. 3, or we can even say, yeah, let's go ahead and do this. 3x to the 0 power. Well, the 0 power, think of it sometimes kind of like a balloon, where that exponent is attached, right? You don't want your balloon to fly away, so it has to have that person holding onto the string, or in other words, the base. So the 0 here, it would be floating away, but it has the base of x. So that exponent of 0 is only going to affect the x. The 3 is not. X to the 0 power will, again, because of that rule, anything to the 0 power is just 1. It'd be 3 times 1, which is 3. So out of all these, that's a super important rule to remember. Let's go ahead and take a look at the other ones here. So this one, again, this is how they'll use the expression. B to the 1 power is equal to b. Anything to the 1 power is itself. But again, this is how the statement would be written verbally, to the power of 1. B squared, or b to the power of 2. That's another way. B cubed, again, because it's to the power of 3, or b to the 3rd power. And then depending on how many b's you have written out, and whatever number, like say you have 5 b's written out, right? B to the 5th power. So or b to the power of 5. Either way, both of those expressions are acceptable, and that's how we reference to these. Again, exponents, that floating number, and then you have the base. So I probably should have went over that a little in the before I started covering b to the 0 power. So that exponent cannot exist unless it's had its base. So like I said, I think of it kind of like a little balloon where the floating number needs to be attached to something. So this 3 or that exponent of 3 is attached to the base of b, meaning it only affects b. So you'll be looking at like some pretty, they'll have more expressions into it. So like 4x squared y to the 5th. Keep in mind that, so when we're looking at these, this 5th power is attached to this y of the base. That 2 power is attached to the base of x. This one, that 4 does have a power, but again, that's our invisible 1, which is right here. But anything to the 1 power, we just prefer not to write it, the 1 there. Let's go ahead and move on to slide 18. So these are the properties of exponents. So this one, I do highly suggest that you go ahead and write these down in your notes because they're going to be super handy when we look at the next couple of sections or the next couple of slides. I'm going to give you the example, but also with numbers, because I know when we're looking at this with letters, sometimes it's a little bit confusing and not everyone's a fan of it, and I completely understand. So I'm going to give you, so product of powers is, well, the first one we're going to look at. Again, you can write out the formula. You can write the formula, and then you can also write the example that I'm going to provide you. So this next one right here is a to the n power a times a to the n power. Keep in mind, the base is a. They have the same base, so you can write it as one base, m, this exponent plus that exponent will be the total. So again, let me give it to you and with actual numbers here. You can have, let's say 3. 3 to the 4th power times 3 to the 2 power. Since I already have the same base of 3 and 3, if we follow along to that property, the properties of exponents here, a product of powers, I can write the same base 3, and because they're the same, we can add these two exponents. That's the rule, adding. So right here, we would have 4 plus 2, or when you add that, you get 6. So this will be 3 to the 6th power. So if you want to look at it expanded, 3 to the 4th power is the same thing as 3 times 3 times 3 times 3 times 3 to the 2 power, 3 times 3. 2 of them right there. So this is 3 to the 4th power, 3 to the 2 power. Again, you're all multiplying. If you count up all your 3's, you still get the same value of 3 to the 6th power. So my preference is that first one that I wrote, or that first line, because that second one, imagine you had 3 to the 10th power. Writing out 3 10 times is a little bit too exaggerating, right? Or a little bit time consuming. Let's go ahead and take a look at the next one. Power of a product. So here you have A and B inside the parentheses, and it's raised to the power of m. That m will get distributed into those into both of those variables of A and B. So how does that look like for here? So here's my my example. We have, let's say, 2x to the 4th power. That means this 4 power has to get distributed, or instead of, well, yeah, let's leave it as 2, and I'll give you another one with 2 variables. So that 4 has to go to the 2, this 4 has to go to the x. So we can rewrite this expression as 2, right, to the 4th power times x to the 4th power. So that power gets distributed inside. Now, I kind of jumped into a little bit of the power of a power, but let me give you another example before we move on to the next one. Let me go ahead and give you another example with like variables. I know we already have A and B, but we can use the common ones that we normally see, x and y. X and y to the 2 power. Again, that 2 gets distributed to the x, that 2 gets distributed to the y to get x squared y squared. Power of a power. Moving on to that next one. A to the m power raised to the n power is the same thing as a m to the n. So what if my a is, let's just say, 5 to the 2 power? And then this is wrapped in parentheses, 5 to the 2 power to the, let's say, 4th power. So the rule is, I already have an exponent there, but remember I have to distribute this 4 exponent inside. This 4 and this 2 are going to multiply to each other. So the base here will still be 5, but when we multiply 2 times 4, right? 2 times 4, we get that 8. So this is in reality 5 to the 8th power. So when you go from here, you can kind of straight jump into this right here. You don't have to rewrite it, but again, it doesn't hurt to write out all your steps again, because sometimes if we get something wrong, we want to go back and see where we made that mistake. Let's go ahead and talk about quotients of powers. So when we are dividing, which I probably should have done right after the product of powers, the only reason I wanted to go back to that is because when we are, well, we'll talk about that after. I'll make the note of it. So let's take a look. A to the m power, a to the n power. Again, we have the same base of a, but again, this is in quotient form. Do you see? We're going to subtract the exponents. The top exponent minus the bottom exponent. So please keep that in mind. It's the top minus the bottom here. So again, let me go ahead and write this in numbers. Let's say this is 5 to the, let's say, 5th power. And let's say this is 5 to the 2 power. So what we're going to do here is, well, we can write it the long way. But again, it's not always my preference, but 5 to the 5th power, we're going to do it the long way, and we'll see the shortcut after, meaning that property. So that's 5 times 5 times 5 times 5 times 5, all over 5 times 5. All I did was just expand. 5 to the 5th power is just writing 5 times. 5 to the 2 power is writing 5 2 times. And if I were to simplify this, 5 cancels out with this 5. This one cancels out with this. I'm left with at the top 5 3 5s. Or we can rewrite this as, oops, let me squeeze it in there, 5 to the 3rd power. But again, with this property, I don't have to do all this work, right? I know that they have the same base of 5. I do the top exponent minus the bottom exponent. So the top exponent is 5 minus 2. 5 minus 2 is the same thing as 3. It matches this answer to this one right here. Again, this is a long way. If you want to do it this way and you're more comfortable with it, go for it. But again, you should start getting used to this, the property rules where you kind of jump straight into this, because that's going to help you when you're simplifying some of these expressions, which is kind of a hint of what you're going to be seeing in the next couple of slides. Now let's go ahead and talk about power of a quotient. It is very, very similar to power of a power, where power of a product. So they're kind of side by side. This m got distributed to a times b. What if you're dividing them? So a and b, you have a power of m. The m gets distributed everywhere inside those parentheses, even if you're dividing. So again, let's talk about it in an example. Let's just say you have 3 over 4, and you raise this to the, let's say, 6th power. Keep in mind that 6 has to get distributed to this 3 and this 4 right here. So this is equivalent to 3 to the 6th power over 4 to the 6th power. So very similar to power of a product. But again, the product, right, because you're multiplying a times b, the quotient, you're dividing by something. Again, you could even have a variable here. So instead of a 3, we can say that this was y. It'd be y to the 6 over 4 to the 6th power. Going back to that note, the first, or kind of like the first one that you learned, when you're multiplying, do you see multiplying makes a number, should make a number bigger? And what other math operation makes a number bigger? Adding. So do you see that connection? When you multiply, you're adding. When you're dividing, you're making a number most likely smaller. Not all the time, but most of the time, you're making it smaller. What other math operation relates to kind of making a number smaller? Subtracting. So when you're dividing, you're subtracting. When you're multiplying, you're adding. Again, just making a quick note on that. Let's go ahead and discuss. We'll actually wait for this one for the part 2 to this.